Hello, everyone. Welcome to the Topological Complexity Seminar. Today, our speaker is Alexander Dranishnikov from the University of Florida, and his topic is on the LS category of group homomorphisms. Take it away, Sasha.
Thank you. Now I'm gonna try again to share the screen. I hope it worked.
Yeah, it's good.
And okay, I'm gonna start from the definition of Lusternik-Schnirelmann category. Just recall everybody knows, of course, the category of X, and we assume that X is ANR space, a nice space, is a minimal number K such that X admits an open cover by K plus 1 sets, which each is contractible in X. So this definition of reduced category. Definition comes from late 20s. In 40s, Ralph Fox proves that you can use closed sets. Actually, in the original definitions, Lusternik and Schnirelmann, they use closed sets, and Fox proves that you can use open. And just like about 6-7 years ago, my student Tulsi Srinivasan proved that you can use any sets, still with the same definition. There are many good properties of LS category, and first of all, it's a homotopy invariant, and then the category can be defined for discrete groups. The category of a group is just category of Eilenberg space K gamma 1, the category classifying space. So all classifying spaces are homotopy equivalent, so the category of a group is well defined. But it's not really interesting invariant because Eilenberg and Ganea proved that the category of a group is the cohomological dimension. So it's known that cohomological dimension of groups with torsion is infinite, so it makes sense to consider category only for torsion-free groups. And in this talk, we're going to consider only torsion-free groups. So just let me recall definition of cohomological dimension of a group. It's a maximum of K such that K-dimensional cohomology with coefficients in some Z gamma module is non-trivial group. And that definition can be reformulated in terms of Bernstein-Schwarz class. It's one-dimensional cohomology class of group with coefficients in augmentation ideal. And it's universal in the sense that for any element of cohomology, group of a group with any coefficients m, there is homomorphism of some tensor power, corresponding tensor power. So if you have K cohomology, so K tensor power of augmentation ideal, tensor over Z, and homomorphism, coefficient homomorphism phi, such that K's power of Bernstein-Schwarz class goes to your chosen element alpha. So this really universal class, it generates all the cohomology with different coefficients. And actually that class can recognize any homology. For any homology with local coefficients, corresponding power of that class, evaluated on this homology class is non-trivial. And now the definition of cohomological dimension of a group can be just restated as a maximum of K such that K's power of Bernstein-Schwarz class is non-zero. In 40s, Ralph Fox introduced the definition of a last category of a map. It's natural definition, and the category of a map from X to Y is a minimal number K such that X admits an open cover by K plus 1 open sets, and restriction of F to each of them is null homotopic. And say for Lusternik-Schnirelmann category, it's well-known lower bound called cut lengths, and the same bound works for maps. If you have product of lengths K of non-zero cohomology classes with any coefficients in Y such that F star of that product is non-zero, then the category of F greater equals than K. And it's basically the same proof as for just category of the identity map. And then we can define, if you have a group homomorphism, you can define the category of group homomorphism to be the category of a map F that between classifying spaces of the groups such that such map which on the fundamental group level is our homomorphism phi. So for any homomorphism phi, there is a map of between classifying spaces of groups such that the induced homomorphism equals phi. Now, question: what is cohomological dimension of group homomorphism? And I guess Mark Grant about a decade ago defines that first as maximum K such that induced homomorphism for K-dimensional cohomology is non-zero for some lambda modulo M. So that definition, as in the case of cohomological dimension of a group, can be restated in terms of Bernstein-Schwarz class. Bernstein-Schwarz class of the target group, and cohomological dimension of group homomorphism is maximal K such that the image of K's power of that Bernstein class is non-zero. And clearly, cohomological dimension of group homomorphism is a lower bound for the category. So it's the same, like this proposition about cup lengths implies that. Okay, and now, yeah, just I believe it's natural conjecture that, like in the case of Eilenberg and Ganea theorem, the category of group homomorphism should coincide with the cohomological dimension of group homomorphism. So I just asked my student Jimmy Scott to check that, and he proved it's in the case when phi is injective, it's a group monomorphism. And he proves that when groups involved gamma and lambda are free, and when they are pre-abelian. And later on, I believe with the help of Mark Grant, discovered that there was Tom Goodwill is a counterexample to this conjecture. Example is, well, group homomorphism of some group G onto Z squared of cohomological dimension 1 and of Lusternik-Schnirelmann category 2. But that group is infinitely generated. So what I want to present in this talk, some new result on that conjecture. They joined with my another student, Nursultan Kuanishov, a current student. Jimmy Scott already graduated. So, and we proved two theorems. The conjecture holds true for torsion-free nilpotent groups, and there is a counterexample for in the case of geometrically finite groups. So there is group homomorphism between geometrically finite groups, and such that conjecture doesn't hold true. So it means CD of that homomorphism is strictly less than cut as in the category. And moreover, these geometrically finite groups are fundamental groups of manifolds. And just proposition, it's I believe it's well known that in the case of group, the category of group homomorphism is minimal number k such that corresponding map for classifying spaces can be deformed to k-dimensional skeleton. Just to see category of group homomorphism geometrically. So in a sense, you can define a dimension of group homomorphism, a geometric dimension, and in a sense, it's geometric dimension, and it coincides with geometric dimension. So in my talk, first I'm gonna present Goodwill's example, slightly modified. Then I'm gonna discuss the case of nilpotent groups, and then example of aspherical manifolds. So Goodwill's example, we consider, pi is just denotes z squared, and we consider group extension of pi by tensor power of augmentation ideal, the tensor square, and using Bernstein-Schwarz class, universal class, and its square. Then, if you have an extension defined by some cohomological class, the image of that class is 0. Since it's universal, it follows the cohomological dimension of this phi, which comes from that extension, is at most 1. Well, of course, it's 1. But if you look at the classifying spaces BG and BPi and corresponding map, the map cannot be deformed to one-dimensional skeleton. If it deformed, then phi factors through a free group. And since phi is epimorphism on z squared, so a group with two generators, that it means that that free group has rank at most at least 2, and then since it's free group, and you may in that factorization you may assume that you have factorization. Psi is also surjective. You may assume that. Then it follows that G is supposed to contain F, free group of rank 2. But group G is amenable, since it's a billion by a billion extension, so it cannot contain a free group, cannot contain F2. So it means the category of phi is 2. So it's a nice example, but yeah, G is infinite dimension, infinitely generated. Okay, say next. Reduction of the whole conjecture to group epimorphisms. So if you consider arbitrary group homomorphism, you can factor that as first epimorphism, then the inclusion monomorphism. And the following theorem is not difficult to prove. For any group homomorphism, say when you factor, say, group homomorphism phi, the first homomorphism denoted by phi prime, which is epimorphism. And for any group homomorphism, the category of phi equals the category of phi prime, and cohomological dimension of phi equals the cohomological dimension of phi prime. So you have to clearly say this inequality holds true. So it means you have to prove inequality in the other direction. In the case of category, it can be done using Ganea's approach to Lusternik-Schnirelmann category. And the idea is just if you have a subgroup, gamma prime of group lambda, you have the map, it could be considered as an inclusion, doesn't really matter, which relies that inclusion J of subgroup. And you consider universal cover and pull back. And then the claim is that there is a lift of P prime with respect to universal cover of the subgroup. And it follows from easy diagram chasing that this homomorphism, this homomorphism, this one for fundamental group is trivial. If you take a loop in this pullback, it goes to 0 because here you have inclusion, J is inclusion, and here universal cover of B lambda is simply connected. In the case of cohomological dimension, again you have this inequality, and to prove the other inequality, just basically Shapiro lemma. So if you know that cohomological dimension of phi prime is k, so it means there is non-trivial homomorphism for some coefficient group, for some module, and you consider this diagram where C is co-induced module, and so you have yellow here, Shapiro isomorphism, and this is non-zero, so it implies that this homomorphism is non-zero. So it means the conjecture is basically the conjecture about epimorphisms. And so we consider that conjecture for nilpotent groups. And let me show what are the difficulties there for nilpotent groups. Say, let us consider example of a Heisenberg group and natural epimorphism onto this square. Well, say this homomorphism can be realized as a fiber bundle F, which comes from the pullback. This pullback diagram, where H is a Hopf map, Hopf bundle. And then this diagram implies that that induced homomorphism is zero for two-dimensional cohomology with integral coefficients. So it means to prove that, to show that the category of phi equals the cohomological dimension of phi. So it suffices to show that cohomological dimension is 2, but you cannot do that with constant coefficients. So you need to use local coefficients. And the idea how it can be done, if you consider universal cover and the pullback diagram here. So in the pullback diagram, pullback is a product of the plane across the circle. And this implies the following commutative diagram. Vertical arrow, this is well known. There is isomorphism between cohomology of classifying space with z pi coefficient and to the cohomology with compact support of the universal cover. And this is actually on isomorphism on cochain level. Well, in this case, on the left, you also have homomorphism. You have commutative diagram. And what you have, this isomorphism, and this for cohomology with compact supports is injective. It's because you have proper retraction here. It's the space is S1 cross the plane. And it implies that this homomorphism is injective. And this is the idea. That idea is extended to all nilpotent groups, and we did that by induction on. But first of all, the main lemma which is needed. And I wasn't able to find that in literature. So any epimorphism between torsion-free finitely generated nilpotent groups can be realized by a fiber bundle of closed nil manifolds. So of course it can be realized by a map between nil manifolds, but it's actually can be realized by fiber bundle. And say, let me recall Maltsev completions theorem. If you have torsion-free finitely generated nilpotent group gamma, then gamma can be realized as a fundamental group of closed manifold called nil manifold. And the proof of the main lemma is not really straightforward. It doesn't really immediately follows from Maltsev's theorem. So it turns out to be quite technical. The proof is done of main lemma by induction on the sum of nilpotency classes of these groups, and this recall just in case nilpotent group is nilpotency class is what you have upper central series of a group. So just start with the center and then consider next quotient group by the center and the center of that and the preimage and so on. And nilpotency class is minimal m when the n is gamma. And say we use upper central series in our proof because of the fact that if you have torsion-free finitely generated nilpotent group gamma and factored by the center is torsion-free finitely generated nilpotent groups. So it's nilpotent groups and finitely generated is obvious. It's torsion-free. It's not exactly obvious. It follows from some old multiple results, but they're not trivial. Well, and now our first theorem. If you have epimorphism between torsion-free finitely generated nilpotent groups, then the category of that equals the cohomological dimension and equals the cohomological dimension of the image of lambda. And the proof using the lemma, main lemma, it's basically the same what I showed you in the case of Heisenberg group. So you just go to the universal cover and consider of the image. So you realize that homomorphism by fiber bundle of nilpotent groups, and the pullback is homomorphic to the product of the universal coverage homomorphic to Rn cross closed manifolds, and it follows that it implies that you have monomorphism here, and again with z lambda coefficient you have monomorphism here. So this that's it about nilpotent groups. Still, there is an open question even here. You can consider nilpotent groups with torsions. Say, of course, cohomological dimension of such group is infinity, but you could have the situation when cohomological dimension of group homomorphism is finite, especially when you have group homomorphism of torsion-free nilpotent group onto torsion nilpotent group. And since this problem is still open, since no classification of finite nilpotent groups, P groups, and there are other difficulties there. So that's it about nilpotent, and I moving to my favorite stuff in that project, manifold counterexample, a spherical manifold counterexample. And let me recall, Gromov's conjecture, published in '96, classifying map of inessential and manifold can be deformed to n-2 dimensional skeleton of B pi. Here pi is a fundamental group of manifold, and classifying map is the map that classifies the universal cover of basically any map which induces isomorphism fundamental groups. And manifold is called inessential. It's the definition of Gromov if the classifying map can be deformed to n-1 dimensional skeleton. So Gromov conjectured that if you can deform manifold to n-1 dimensional skeleton, then automatically you can deform it further. And that conjecture came from his research on positive scalar curvature. Now, published in '06, by another collaborator, Bolotov, gave the following example. There is clause for manifold this fundamental group pi, which is free product z and z cube, such that classifying map cannot be deformed to two-dimensional skeleton. And note that classifying space for this pi is just a wedge of the circle and torus. So it is three-dimensional. So it means manifold is inessential because it's four-dimensional. It's already deformed in a three-dimensional skeleton. And construction of Bolotov example is the following. Again, we consider Hopf bundle and manifold n, which is connected sum of a product of two-dimensional sphere and a circle and three torus. And define a map of that to the sphere. Just first collapse that three torus and then project onto the sphere and take the pullback. So this is Bolotov's example. Now I need the following properties of that example. First, if you consider induced homomorphism for the fundamental groups, then this is isomorphism. It follows that, if you consider homotopy exact sequence of this fibrous circle, it follows that the fiber circle, the fiber is null homotopic in M, and it implies that it's isomorphism, and of course it's epimorphism. So next property that for three-dimensional cohomology, classifying map of U of that manifold M is trivial for any pi module. And the proof of that also it's just Poincare duality and universality property of Bernstein-Schwarz class. So if you take an element in cohomology group and assume that image is non-zero, then you consider a Poincare dual class. So manifold is four-dimensional, this three-dimensional, so this one-dimensional homology class. And it can be detected by Bernstein-Schwarz class. It's not a cohomology element of a group, it's an M, but it's in dimension 1. And since U is isomorphism on the fundamental group, so it means that detection in the group can be translated to M. So you have the image of Bernstein-Schwarz class under that isomorphism. This is isomorphism in dimension 1, and it detects that. Well, what you have here, that the image of the cup product of A and the Bernstein-Schwarz class is non-zero, which is impossible. By dimensional reason. B pi is three-dimensional and A was already three-dimensional, so contradiction. Now, another property that the map U followed by projection of the circle in classifying space to point, so map to three sphere is essential, is not null homotopic, this map. That requires some argument, and maybe I'm gonna bring some ideas at the end. And one more property what I use is M is stably parallelizable. Well, N here is stably parallelizable as connected sum of two stably parallelizable manifolds. And what is M? M is total space of orientable circle bundle of a stably parallelizable, so it follows it's also stably parallelizable. Okay, now, the following lemma. Suppose that F is a map of degree 1 between closed stably parallelizable manifolds. Then for the stable cohomotopy groups, the induced map is injective. It's classical lemma for a map between orientable manifolds, map of degree 1. Then for cohomology, induced map is injective. Here we use generalized cohomology, stable cohomotopy groups. For that, the same proof of that lemma, classical lemma, works for generalized cohomology. But what you need orientability of manifolds, and with respect to this cohomology theory. But manifold is orientable with respect to stable cohomotopy groups, stable homotopy groups theory, if and only if actually when it's stably parallelizable. So whenever you have a map of degree 1 between stably parallelizable manifolds, so you have the fundamental class and you have duality, and the same proof that F star is injective works. Another ingredient I need for that, it's just combination of this theorem. It's idea of hyperbolization of manifolds. It comes from Gromov. First construction, detailed construction was done by Davis Januszkiewicz, and then real hyperbolization construction was done by Cherny and Davis. And say this combined formulation is the following. For any closed orientable manifold M, there is a map of degree 1 of closed aspherical manifold, which is surjective on the fundamental group. Yes, I forgot to mention that. It's also stably parallelizable. There is a map of degree 1 spherical and manifold is stably parallelizable if M is stably parallelizable. And now I have all ingredients to prove theorem 2. So there is a map of closed spherical for manifold onto 3 torus such that for the fundamental group induced homomorphism G star cohomological dimension is strictly less than the category. And say how one can prove that the category of this map is 3. the idea is to show that homomorphism, well, first of all, by lemma, this homomorphism for three-dimensional cohomotopic groups is injective. And say if you look at three-dimensional cohomotopic group of M, it's just homotopic classes of maps to three sphere. And now, yeah, that was one of the properties that, let me just show again these properties. Yeah, property C. For M, if you consider classifying map and then collapsing to three torus, so it means that map what we consider in our example, and then just degree one map onto three sphere, that map is essential. So it is essential, so it means it defines some element of stable cohomotopic group of M, and since it's injective, so it means this homomorphism is non-trivial, so it means this map, through map G, is essential. And if you look at three-dimensional cohomology, we prove that U star is zero homomorphism, so it means G star is also zero. This is actually the end of the proof, and yeah, I plan to show the proof of that property C. But it's quite, it's abstraction theory. And since it's secondary abstraction, so it deals with Stingray squares. Yeah, I mean, if some of you want to listen to, I'm probably gonna present it, but I would prefer to stop here. Thank you.
Okay, are there any questions? Yeah, we should do that. Any questions at all? I think this is an interesting thing. Mark?
Yeah, I could ask a question. So, you said that the category of a homomorphism was somehow like the geometric dimension.
Yeah.
And we have examples of homomorphisms of geometric dimension 2, I guess, and cohomological dimension 1. So it's kind of tempting to think there might be some construction which takes a homomorphism and produces a group. And you could kind of try and produce potential counterexamples to the classical Eilenberg and Ganea. So you're nodding, so you've thought about this.
Yeah, actually, I thought about that. Taking like something like inverse limit, say if you do this construction, say this construction is cohomological dimension 2 and geometric dimension 3, and takes it inverse limit, but I mean I cannot do the second step. I thought about that. Yeah, say
what kind of inverse limit? Sorry.
Well, say I don't know. I mean, I started from three torus, and above you have four-dimensional manifold. But next step it should be something like again four-dimensional mapping through something three-dimensional which goes to that W. But that inverse limit, it's not really finite. It's not really discrete group. Other way would be taking direct limits, but direct limits then would be problem to show that geometric dimension is, oh no, cohomological dimension is 2. It could jump up. So yeah, it's a good speculation. Actually, I thought maybe I should mention that. I don't know. It's could be an approach, but I don't see really how it could be. But yeah, say some topological ideas hidden here. They work only in this dimension, I think. So it looks like it could be.
Okay, thanks.
Okay, any other questions? Okay, I'm going to stop the recording here.